So, hi guys, this is Dr. Edwards again, and now I want to talk to you to some extent about um, minimum, maximums, and SaddlePoints. I'll get to that in a moment, but firstly, let me just have you recall the notion of a simple first order derivative. The derivative of f of x with respect to x is this limiting process, as we all remember from our basic calculus. And it can be written in this way, that the differential of f, you put x on the dx on the right hand side of the equation. Df then is the function at x plus dx minus the function at x, which is equal to df dx dx. Obviously so, because you can cross dx with dx here and you get df, so df equals df. No big deal. When f is a function then of more than x, say x, y, and z, then the differential of f is equal to the partial of the differential of f with respect to x dx, partial of f with respect to y dy, plus the partial f with respect to z dz, where the function is a function, f is a function of x, y, and z. So we call these partials, as you remember. We've already talked about these previously as well. Let me go on. We also have this expression, will come up from time to time. This is the partial having been taken with respect to x, and then you take that results with respect to y. So this is the partial with respect to y, or the partial of f with respect to x. And so the same will be true. We call this a cross derivatives or mixed derivatives, these expressions. It should not matter which come first. You take the partial with respect to x firstly, or take the partial with respect to y firstly, and then with respect to x or vice versa, you should get the same results. Let me go on now. And the change rule is there. Now let's talk about these stationary points. Read through all of this on your own, but whenever there's going to be a stationary point, the derivative of the function at that point is going to be 0. All right, however many points there are, wherever that there is one of these extremas, minimum, max, or saddle points. All three of those are called extremas. The partial of the function with respect to the variable of reference at that point should be equal to 0. Okay, now let's go on a bit further here. Saddle points. I want you to see this image here. What is going on here is that there is an extrema here. Now, if you go along the y-axis this way, you can see that there is a maximum of the function along the y-axis. But if you come along the x-axis, there is a minimum. So that's how it is at a saddle point. It's a max along one axis, and you can see here it's a minimum then along the other. That constitutes a saddle point for obvious reasons why it is called a saddle. Now let's go on. Let me give you then, and interesting as we pass, as the Maclaurin expansion is here, you can think about, you can expand a given function in terms of powers of x, powers of y, power of x times y. So you can expand any function, any well-behaved function using the Maclaurin series. And these are the binomial coefficient that you can find the values of. All right, we wanted to give that in passing. Now, what I'm going to focus on now are functions that are a function of 2 dimensions only, x and y, or x and z, or z and y. But here I'm going to focus and illustrate this first illustration with a function of x and y. So therefore, you can think that there are local minimums, local maximums, and or saddle points in this space where these functions exist. Now let me then go through the process, a systematic process, which will allow you to determine whether it's a minimum, max, or saddle point. Okay, let's go. So this is the function. All right, so this is the first. You just write the function as a given. Capital X of x is the partial of f with respect to x. So you take the partial of this expression with x, you get 3x squared minus 6y, obviously. So you take the partial of the function with respect to y here, and you get then minus 6x plus 24y squared. All right, so we've identified all of the first partials. That's the first step. Now, as I said, the first partials have to be 0 wherever there's a saddle point. Oh, I'm sorry, where there's a critical point, whether it's a saddle point or minimum max. So let's see here. So to take the first one, you set it equal to 0. That means then at that critical point, as you can solve here, 1/2 x squared is equal to y. And for the other expression, you solve here, you set this equal to 0, and you get then minus 6x plus 6x to the 4th. That too must equal to 0. Then you can separate it, you can factor here, you factor out 6x, and you solve for x. One place, x can be 0, and this expression is satisfied, or x can be equal to plus 1. There may be some imaginary roots here, complex roots, but we're looking for the real roots here only. All right, so now these are the two locations where there's a extrema. That's the first part. Now, what is the corresponding value of x, where these corresponding value of y for these x values? So you just go back here, you substitute now in the value of the x, put in x here, and you get that y equal to 0. You put in this value, x equals 1 here, and you get that y equals to 1/2. So therefore, you have located now the two critical points. One point is at x equals 0, y equals 0, that's one point. The other at x equals 1 and y equals 1/2. That's the other point. Now, what you also want to do now is go on and take the second partial. So you take the second partial of f of x, and you get here 6x. You take the second partial with respect to y, and you get then 48y right there. And you take the mixed partial of either one of these, and you get -6. All right, so you're getting there. These are some of my individual notes, but I'll just follow the author. Here is the discriminator right here. When D, we call it the discriminator, and I haven't shown you why this is true, but it is. So D, we call it, is equal to the product of the two individual partials, second partials, minus the square of the mixed partial. You see what I mean? That is called the discriminator. And when the discriminator is greater than 0, and the second partial with respect to x is greater than 0, the function in question is a local minimum. When the discriminator is greater than 0, and the second partial with respect to x is less than 0, the point is a maximum. And thirdly, if the discriminator is less than 0 right away, no other conditions have to be considered, that point is a saddle point. All right, so for what we've done here, let's then consider the critical point x0 and y0. If you go back and substitute everything in, f of xx is 0, f of y is 0, minus then the quantity of the mixed partial squared, and you get negative 36. There it is right away. That x equals 0, y equals 0 is going to be a saddle point. Now let's go on. For the point x equals 1, y equals 1/2, the discriminator is equal to 6 times 24 minus the quantity 6 squared, which is positive. So therefore, the point x equals 1, y equals 1/2 could be minimum or max. Let's go on and we will find which is which. So let's see here, let's see. So for right here, b is less than 0, but that's a saddle point. But what about now if you put in for x equals 1 and y equals 1/2, you get 108. But then if you calculate f of xx at that point, x equals 1, y equals 1/2, you get that f of xx is equal to a value that's greater than 0. Therefore, you're in this situation here, so that quantity is a local minimum. There you have found then that for the critical points, x equals 0, y equals 0 is a saddle point. For the critical point, x equals 1, y equals 1/2, it is a local minimum for this problem. So what I will do then, I'll give you several such functions of this kind or that kind. This is the same expression. And I want you to be able to tell me, based on this recipe procedure that I've given you here, whether or not the critical point is a minimum point or a local maximum or saddle point. Okay? Go through these presentations here and understand them and work through the homework problems. Have a good day.